So we were doing this sampling with another replacement in the last class. So the idea is that we have a small town of 5,000 residents, 1,000 of whom are under 18. So we choose 4 of them at random and ask how many people are under the age of 18. So now there are 2 ways of doing it. One way is that you can say is that after picking everybody, I put that person back in the population and I pick again. That's with replacement. So everybody is available selection in each trial. So you think a little bit, that's just like choosing. So you have a total of 1,000 whom you're interested in, and there are 5,000 of them. So 1,000 by 5,000 is 1 by 5, and that's why you get independent Bernoulli 1 over 5 times. Then the other option is that once you pick a person, you don't put the person back. So without replacement. Without replacement. So here, if an individual is chosen, the person is no longer available for selection. There are 2 methods of doing it. So the first method we have seen. So let's say if you want to understand the question that exactly 2 of them under 18 from the 4 that you have chosen. So the way one does it is, you think of it in the following way. You have 5,000 choose 4 ways of choosing 4 residents 5,000. Each way is equally likely. Selecting 2 of them under age of 18 is 1,000 choose 2 times 4,000 choose 2 ways. So the net probability is going to be 1,000 choose 2, 4,000 choose 2. So that's the answer you get here. And then what we found out was that if you did independent Bernoulli trials, that is, if you chose them with replacement, then the answer would be 4 choose 2, 1 over 5 choose 2, whole past 2, 4/5 whole past. And then if you do the computation, the answer in red turns out to be kind of close by. So the key thing is that the 2 methods are very different. So one is without replacement, and one is with replacement. And in one case we have independence, in the other case we don't have, but the answers are not so far away. So this is kind of a very useful idea used in statistics a lot. So the idea is the following, that so sampling with replacement and sampling without replacement So there are 2 different, are very, they're sort of so let me write down this way, not this way. Sampling with replacement and sampling without replacement. Without replacement. The 2 methods, so let's start on the 2 methods. The 2 methods so I should say let me write down that we have not shown a proof for this. Give similar answers if the sample size is much smaller. What is much smaller? We don't know. It's much smaller. We don't know. It's much smaller than the total population size. So let's say the population size. Then the populations become. So of course, this is something that I have not shown a proof for you, but that's the formal idea. This with replacement and without replacement, they're two different methods. They give two different answers, but the methods give similar answers if the sample size is much smaller. So this is a sort of a, if you do statistics, this is a key fact that's used in statistics a lot. So again, like before, when we did this n go to infinity and we computed the probability of AK, and I said that it goes to this Poisson. Similarly, the above is also can be thought of a distribution. This quantity right here, this 1000 choose to the above of 5,000 choose 4. So the distribution is called hypergeometric. So we'll write it down. So it's called hypergeometric distribution. And it has several parameters. So one is capital N, is like the 5,000 people. Then it has little r, which is in our case the number of people who are below 18, and m is the sample size of the pictures. Let me write this in blue so it's clear. So in r and m. So the idea is that let me write the whole thing in proper form. So n is the number of people or not size of population. So number of population. So this could be people, could be balls, could be, and then R is the number of people, number in population, number in population with a certain characteristic. Certain characteristic. And then m, little m, is the number of the sample chosen. So here's the key without replacement. So you choose m from the population without replacement from capital N people, and R of whom have a certain characteristic. Of course, I mean, what you're interested in is the number of people with characteristic R. Of course, your M has to be less than R. Otherwise, if it's more than R, then you can't. You pick more people outside the characteristic. So then let's write this down. Let's say S. So S is the sample space. S is going to be you can have 0 successes, 1 success, so on and so forth, and up to so at the most R. So what we'll do is, so we'll, let me just backtrack a little bit. So before I set up the sample space, so what can you do? You can pick at least 0, maximum of 0, and just to be mathematically precise, I will write it as m minus n minus r. That way I don't have to fix what R and then R. So S is from here. It starts with this number, and then it goes all the way till the minimum of m and r. That's the number of people I can pick in my sample, and the chance of picking k people with characteristic R with replacement, the sample with replacement. So let me erase this. Then sample with replacement. And the sample is of size n. Sample is of size n. and the population is of size capital N, and there are R people with characteristics. So, so let's say certain characteristics. So I won't say characteristic R. So let's say characteristic. Let's call it characteristic. Let's say capital R. So here I'll have to say capital R. So what do I get? This is going to be equal to. So it's going to be. I have to pick the k people from little r or choose k. And the rest of them had to be chosen from n minus r. I had to choose them with m minus k. And the number we are choosing k people is just n choose. And m people is just m choose. So that this is called the hypergeometric distribution, and you can think of this as this probability of k or probability of k people. This probability of k this is defined as this is how you think about this probability, and the answer is this for any k. So of course, one needs to check. This is some exercise you can think about. Is it a clever way of check? Up to now, the way I set up the experiment, it's kind of clear that this is exhaustive. But one exercise to check is that is it really a probability? That's predefined probability. So so does the question is that the exercise is that does P define a probability? The idea is that can you show that summation k in S, the chance of k is actually equal to one? I mean, think about it. So then show that P in D is a probability. So this is a very important distribution, and it's a very powerful one, and it's used widely in applications. Hypergeometric means without replacement, and be careful that dependencies involved, and that's how you compute the probability. So now let's I sort of was a little glib. So I said that so let's just go back to this idea and try and make some sense of it. Let's try and go back to the observations that I had. So I had said that if I do with replacement, then I get a series of independent Bernoulli P trials. And then I had said here, without replacement, and I had said that this can be thought of as dependent trials. Right? Of course, but I didn't tell you why they were dependent. And dependency is clear because the moment I pick somebody up, the sample is getting smaller, so the dependency is obvious. But can I make this idea rigorous? So let's try and see if I can do this. So I want to make the idea rigorous that I want to think of hypergeometric as a case of dependent Bernoulli trial or dependent trial, not Bernoulli. So let's try and understand that. So this is 2.3.2. This is hypergeometric distributions a series of dependent. So now I want to just try and see how I can do this. So now here, let's try and see how does one do this. So let's go to our previous problem, our previous example. So previous example, I do the same thing. I say that I have 5,000 people. I have 5,000 people, and that's the population size. And I knew that 1,000 of them are under 18. Are under 18. Of 18. This is what we had before. And then I said that, okay, fine, now I'm going to go and pick 4 people. So choose 4 people without replacement. And suppose you want to set it up as dependent trials, the way one would do it is you would first do the following. Let's try and do it. So let's see. So again, we want to do the same thing. Our event of interest E is that there are exactly 2 of them, 2 of the people, 2 of them under the age of 18. That's again our event of interest. So how do I do this again? Now what I do is, if I want to set up, before I know the answer to this, it's just 5,000. If 1,000 choose 2, 4,000 choose 2 divided by 5,000 choose 4. But I want to set it up as a set of independent trials. So what I do is, I say I take j equal to 1, 2, 3, and 4 to index my trials, index my samples. Or index sample. Then what I do is I define AJ as the event is that the jth selection. So that means of sample, I just say index my selection, and that's our selection. Then AJ is the fact that the jth selection is a person younger than 18. Okay, that's the selection I have. So I choose 4 people, but I just order it in this way. So now let's go systematically. 1,000 people are there. I want to look at probability AJ. So first step is clear. Probability of A1. A1 is clear, right? A1 means that the first selection is under 18. So that's clear. So that's just I have 1,000 people to choose who are my favorites, and I have 5,000. So it's 1 over 5. This is exactly the way I would have computed the Bernoulli P problem. So the first one is clear. Now the second one gets a little tricky, right? We have done this before. Let's do it again. So now clearly, let's go back here. So after the first selection, 999 are left. Right? So then probability of A2, if you want to calculate, right, you have to do it in 2 ways. Right? You have to do it in 2 ways. So you have to do it as probability of A2. Let's come back to this in a second. So let's do the simpler one. So now let's say I want to do something simpler. I want to do probability of A2 given A1. So given A1. So what's that going to be? That's going to be 999 left. So that's going to be just at the bottom. So now 999 people under 18 are left. So 999 people under 18. Make it clear. 999 people 999 under 18 are left. Right? So I've already chosen one person here. So when I come to this computation, right here, so I'll get is 999 people I have to choose from, and everybody left is 499. So now let's say that means the first one I've chosen under 18, the second one I've chosen under 18, and let's say I chose I look at the third guy whom I don't want under 18 because my eventee is only exactly 2 people. Let's do one particular computation. So a complement given A1 and A2 is going to be what now? After this, there are only at this step there are 998 left, right? 8 left and 18 left. And this step. So, but here I want A3 complement. That means I don't want the person to be under 18. So then I have how many people I have left? I have everybody else left. There is 4,000 of them left. Divide by 4,998. And I come down here and I do the same thing again. So I do the fourth person I don't want to be under 18. And I do the event under which I have A1, A2, and A3 complement. First trial I pick under 18, second under 18, third I don't pick under 18. This is going to be again equal to 399 by 4997. Each time the population goes down by 1, and the appropriate category also goes down by 1, depending on the selection. Then we know this idea, right? We know that probability of A1 and A2 and A3 complement and A4 complement, that's one way of choosing 2 people under 18 in a size of 4. This we did this in theorem. If we go back to this conditional probability theorem 1.3.8, this we know is the same as probability of A1, probability of A1, A2 given A1, probability of A2, A3 complement given A1 and A2, times the probability of A4 complement given A1 and A2 and A3 complement. That's how it's figured out. And that you multiply it out, and what do you get? You get 1000 by 5000, and you get 999 by 4999, and then you get the next one you get is 4000 by 4998, and you get 3999 divided by 4997. That's how you do it. Of course, there are many ways of doing this. There's one way of getting 18 people, getting 2 under 18. So you have to go through all possible ways. Let's do that. So similarly, one can check a probability of A1 complement, that is, and A2, and let's say A3 and A4 complement is also the same product. It's also the same. Next time you can check the same product. It's 1000 by 5000. That's the first one. So maybe you should do differently. Let's do the same thing. Let's try the same product, but if you do the correct order, it's A1 complement first. That's 4000 by 5000. Then it's A1 complement given A2. That's going to be 1000 by 4999. The third one is going to be A3 given the previous two, A1 complement and A2. That's 999 by 4998. And the last one is going to be A4 complement given the other three things, A1 complement, A2, and A3. So you're going to get 3999 divided by 4997. So the products are the same. So you notice that the net product is the same. Even though the order is different, the net product is the same. So we notice that in each ordering, the individual fractions are different. Individual fractions differ, but product is the same. So then then you set it up as a nice dependent Bernoulli trial, where in each selection you pick under 18, but you want exactly two of them. So you do one of these things. One of these things will have a complement. Two of them will have complements, and two of them will have no complement. But any ordering has the same product. So then you can think a little bit. Just the probability of E is just the number of ways of choosing two people from 4, or the number of ways of putting two complements in 4 sets. You get 4 choose 2, and you put the same product up. 1,000 by 5,000, or 999 by 4. You can do anything you want. 4,999, 4,000 by 4,998, and 3,999 by 4,997. Same. So that's the kind of the answer. But this, if you just do some algebra, so this is an exercise. I'll leave an exercise. Algebra. This will exactly be the same as 1,000 choose 2 into 4,000 choose 2 into 4,000 choose 2 divided by 5,000 choose 2. That's how you get it. So that's the kind of the way of phrasing the whole thing as a dependent trial, and then you get the same answer. So it's kind of a nice idea. You can phrase the hypergeometric in the following manner, like I did before, in this example first. So what I did was I said, okay, fine. If I want to think of it as choosing 4 people from 5,000, I'll look at the total number of ways of choosing them. That's 5,000 choose 4. They're all equal likely. The number of ways I can choose my favorite sample is 1,000 choose 2 times 4,000 choose 2. And the ratio is my answer. That's one way of doing it. But I can also phrase the whole thing like a dependent trial. And the way I did it was I said, okay, I look at each selection and I check if the person is under 18 or not. Then ultimately I want only 2 under 18. So I want A1, A2, A3, A complement, and A4 complement. That's one way of getting under 18. Then I compute that expression. I get something using the condition probabilities that we done before. Now, if I reorder the selections, if I don't pick the first person under 18, I pick the second person under 18, third, and then I don't pick the fourth one under 18, that gives me a certain answer. But I find that even though the individual fractions are different, the products are the same. Then all I have to do is just find the number of ways I can put 2 complements in 4 sets. So that's the number of ways is 4 choose 2, and the answer is the same for every selection, every orientation of complements. So that means I get the answer to be 1,000 choose 2, 2,000 choose 2. So that's how you can order independent trials and dependent trials. So let me write a theorem down that sort of that quantifies this in a certain nice way. So the idea that I said that sampling with replacement, without replacement, can be thought of as dependent, independent trials. Let's try to write a theorem down that will tell us exactly how the dependency can be captured. Here's the theorem. So let N, M, and R be positive integers. Okay. And let's just make everything simple. Let's assume that little m is much smaller than r. It's much smaller than so the previous jugglery of the n minus m minus r maximum or something. Let k belong to 0, 1 up here. So now you define p as r by. You define p1 as r minus k by n minus. And you define p2 to be equal to r minus k by n minus. Right. So now let's do the following. You think of capital H as the probability of choosing, let me write down in black, choosing k people, you may use the k as in blue, I'll come back and change k in blue. Choosing k people from n people, so I should not say this, I should just say, let me not go into let the experiment down, let k be the probability, h be the probability, h be the probability that the probability that the hypergeometric distribution of n, r, and m takes the value k. So by this I mean this h is going to compute the probability that I choose k people with characteristic r with replacement in a sample of 5z. Then the following inequality holds. So on one side I have h, on the other side I also have a bound for h. So if I want to compare them with independent trials, on this side I will write down it's m choose k, p1 power k into 1 minus p2 power m minus k. On the other side, I'll write down m choose k, p power k, and 1 minus p1. This is a bound one can show on both sides. So this is something that the mathematical computation one can do, and one can show this. This I will write down an answer. I'll try and see if I can prove it today. If not, maybe today is too late. Maybe next class I'll prove it. But that's the idea that this is a computation one can use to understand two things. So this is kind of the comparison to independent trials. So if you want to know your sampling with replacement, that is your dependent trial. Okay, these are not quite independent because if the p was equal to p1, if p1 is equal to p, then this is Bernoulli. This is like Bernoulli p1. If p1 is equal to p2, this is like Bernoulli p2. Right? So I'll say Bernoulli p1 exactly. P1. Right? So then the question is, when is this true? So when is this true? So now the key thing is that when are your dependent trials going to be like independent trials? So when will P1 be like P2? So the idea is that if little m is small compared to capital M, then P1, P2, and P are all the same. So the key fact is that if let me go up a little bit so you can see the screen. Very good. So the key idea is that if n is much larger than little m, and then if k is of course much larger, much less than k, then this implies this will quotes that P1 is the same as P2 is the same as P2. So in some sense, your dependent trials can be thought of independent trials if n is very, very large compared to little m. And that's exactly what they do in statistics. They don't worry about with replacement, without replacement. They just think of it as independent trial. So you won't pick the same person twice. Even though you're actually doing that, but independence and dependence are almost the same. This proof, I might leave it as an exercise in assignment, and I'll ask you to prove it. But the proof is not so hard. It just follows from what I did before. When I try to understand how hypergeometric was dependent trials with different problems. Okay, maybe I'll stop here.